Let's continue with a few more examples of geometric sequences. So this first one is quite straightforward again. We are given a sequence, we need to determine if it is geometric and then find the formulas for it and find the 50th term. So to start with, we are looking at 14 to 7. Looks like it could be half. 7 to 7 halves. Yes, it looks like we're multiplying each time by 1/2. Let's try that. Times a 14 times a half is 7. 7 times 1/2 would be 7 halves. 7 halves times 1/2 would be 7/4. So yes, we are multiplying by the same thing each time. Remember, that is called the common ratio. So this time our common ratio is 1/2. Our first term right there, a sub 1, is 14. So for our recursive formula, it looks like we need to state that our first term is 14, and the other terms, a sub n, are gotten by saying a sub n minus 1 and multiplying that by 1/2 by the common ratio. And then our explicit formula, a sub n is equal to our first term, a sub 1, so 14 times 1/2 to the n minus 1 power. A lot of times when the r value is a fraction, you will see it put into parentheses like this. Notice this again is an exponential equation, looks like exponential decay because r is less than 1. All right, so finally, if we wanted to find the 50th term, a sub 50, we're going to use our explicit formula again. So 14 times 1/2 to the 49th power. Okay, now we could multiply that out. Once again, 1/2 to the 49th power is repeatedly multiplying by 1/2 will become smaller and smaller, right? Closer and closer to 0. So let's see if I did that. Yes, I did. So I multiplied it out and I got 2.486 times 10 to the negative 14th. Okay, now that means it's point, like 0 point, and then it was 13 zeros, and then 2.486. So in other words, the sequence is getting closer and closer to 0. That number, the 50th term, is not actually equal to 0, but the farther out you go in the sequence, the closer and closer you get to 0. All right, now next problem gets a little more complicated. This is the same type we did in our arithmetic sequences, so we have to see how those work in geometric as well. We're given the second term is 3 and the sixth term is 48, and we know it is geometric. So let's see. We know a sub 2 is 3 and a sub 6 is 48. We don't know a sub 1 and we don't know r, but we do know it is a geometric sequence. So in this one, since we know the second term, maybe we should just write that. So this is a sub 2. This would be a sub 1, but we don't know what number that is at this point. So this is 2, 3, 4, 5, 6. And this number here is 48, right? Now what we do know is that each time to get from 3 to 48, we need to be multiplying by the same thing. So we're multiplying by r, we're multiplying by r again, and by r again. Let me see if I did that right, how many times. So if we multiply by r once, we'll have the third, again the fourth, once more the fifth, and once more the sixth. Yes, so look, I'm multiplying by r 4 times, right? So in other words, 3 times r to the fourth is going to be equal to 48, right? So I'm starting with the 3 that I have. I'm multiplying by r repeatedly 4 times, and you know if you're repeatedly multiplying by the same thing, that's exponential, right? So that's the exponent of 4, and then that does equal to 48. Okay, so to solve for r, we're going to we can divide both sides by 3, so r to the fourth is equal to 16. And then you might know that r is 2 then, or you just take the fourth root, and it's not a square root, it's a fourth root. And there is a fourth root button in your calculator. If you go to math, you'll see, I believe it's just right in math, it'll say there's x root. Okay. The other way, of course, to write that root would be 16 to the 1/4 power, right? 16 to the 1/4 power is the fourth root of 16. R is 2. Usually, these R's will be reasonably easy to find, so you'll probably just recognize them, but you know that 2 times 2 is 4, times 2 is 8, times 2 is 16. There it is. The fourth root of 16 is 2. And then, since we know R is 2, that means, we actually know all these other terms now. 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48. Yes, it's right. We also now know a sub 1, the first term, because we would just divide by 2. So the first term must be 3/2. Okay, so a sub 1 is 3/2. Now that we know that. So now writing our formulas is the easy part, because we have all the information we need. A sub 1 is equal to 3/2, and a sub n is equal to a sub n minus 1 times 2. Our explicit formula is a sub n will be equal to 3/2 times 2 to the n minus 1 power. Okay, I would write it that way. I don't think you need extra parentheses anywhere. It works. They'll usually give you a dot to work with. Okay, let's do one more like that, because I think it can be a little tricky coming up with how to find R. Just given 2 terms in the sequence, and there's several ways to do it. So just do it a way that you feel comfortable with, but I think this is one of the easiest ways to do it. So let's say that we know the 5th term, so a sub 5 is 64, and a sub 8, the 8th term, is negative 512. If I'm flipping from positive to negative, my guess is that my R is going to be a negative number. They're still getting bigger, so my R is greater than 1. But otherwise, I don't exactly know what the R is. I can do it the same way that I did the last one. 1, 2, 3, 4, 5, in a way. So this is the 5th term, 64, and then 6, 7, 8. This is the 8th term, negative 512. Okay, now notice that from the 5th term to the 8th term, how many times am I multiplying by R? Hopefully you thought in your head 3, right? Times R, times R, times R. So this would be R cubed, so it's 64. R cubed is going to equal negative 512. Okay, that's how we get from this term to this term. So I'm going to divide both sides by 64. So that's R cubed is equal to negative 8. Okay, so we need to take the cube root of both sides. Hopefully you know that the cube root of 8 is 2, so the cube root of negative 8 is negative 2. You might be thinking, like, what about I? Or, is this not a real number? No, since it's the cube root, actually it can be negative, because go negative 2 times negative 2, that's positive 4, times negative 2, that's negative 8. So when you're dealing with odd roots, cube root, fifth root, whatever, you can just have negative numbers. That just means the root is negative. Totally works. It's only when you're doing with square roots or fourth roots, they have to be positive or they would be imaginary. Okay, so we found R, and now we still need to find a sub 1, and I don't know if I want to repeatedly divide that many times, 1, 2, 3, 4, I'd have to divide by 2, divide by 2, divide by 2, well, negative 2, negative 2, negative 2, right? So I think I could write my explicit formula. So my explicit formula is a sub n is equal to a sub 1 times r to the n minus 1 power. right? So, and I think I did this in the arithmetic sequences too. If you have a larger number, if you have, higher terms, you may not want to find the first term from scratch. So you can use the formula. So a sub n, we could just use the fifth term, okay? So a sub n is 64. And then we don't know a sub 1, but we actually know the r is -2. And then the n minus 1 power, since we're talking about the fifth term, is the fourth power. Okay? So this is a multiply. It looks weird there, times. So the only thing I don't know if this is just using the a sub fifth term. Okay? I could also use the eighth term. So I can find a sub 1 because that's the only thing I don't know in this equation. So this is 64 equals a sub 1 times -2 to the fourth is +16, right? So times 16. So a sub 1 is equal to 64 divided by 16, that's 4, right? Okay, well, now that I have the first term and the formulas are easy to write. Okay, so my recursive formula is a sub 1 equals 4, and a sub n is equal to a sub n minus 1 times -2. And then my explicit formula is a sub n is equal to 4 times -2 to the n minus 1 power. Okay?